So we were last talking about systems of equations, and we put, I did an example or two where we put these systems of equations into a matrix to solve. Is everybody comfortable with what I did there? Okay, I'm gonna talk a little bit about matrices, and I'm gonna do kind of more of this stuff and build on it a little bit. So we had these row operations. Anybody remember what they were? Row operations that we used on the matrices. We can, anybody tell me the three things we did? Yeah.
Swap any two rows,
Right.
multiply any row by any non-zero number,
Okay.
and add a multiple of any rows to zero.
Right. You can take that. So you can swap any two rows you want. You can multiply any row by any non-zero number you want. You can multiply by zero too, but that messes things up, so don't do it. And you can take any multiple, even zero, of a row and add it to a different row. Those are our three operations. So it turns out that you can always muck around with your matrix a bit and bring it into something called echelon form, which is going to be very useful to us later. So let me tell you what this is all about. An M matrix is in echelon form. If so, it's got to have a couple of properties that I can pick out. Number one, all rows of all zeros, if any, are at the bottom. So for example, if you mess around with your matrix and you get three rows of all zeros, those three rows got to be stacked on the bottom, right? That's number one. Number two, the leading non-zero entry of any row is to the right of the leading non-zero entry of the row above. So the leading non-zero entries kind of go diagonal down to the right. And I'll put up an example of this. And number three, all entries in a column all leading entries in column below a leading row entry, not zero, or zero. Okay, so let me just kind of draw some of these as criteria. Excellent. Okay, so there's the first row. The leading entry is 2, right? The leading entry of this column, or I'm sorry, this row is 3, right? And notice it's to the right of the leading entry. And you can't go just below, you always have to go to the right. So a next appropriate row might be something like this. And then maybe you've got some rows of zeros below. So the leading entries are this, this, and this, right? notice that they move to the right. That's basically it. And so we've got this, and all the rows of zeros are at the bottom. The leading entries move down to the right, strictly to the right, and all entries in a column below a leading non-zero have to be zero. Actually, that follows from the second. Okay. This is what we call echelon form. Now, let's do echelon form on steroids. We're going to actually like this stronger version of echelon form. We say that our matrix is in row reduced echelon form. Okay, so this is echelon form and then some. If also so it has to satisfy these things to be an echelon form, and also for each rows leading non-zero entry is 1, and 5 each leading row entry and here I mean non-zero is only non-zero element in the column. So this basically says something about the leading entries, right? This matrix right here is in echelon form. It is not in row reduced echelon. Right? Can we turn this into row reduced echelon form using row operations? Yes, indeed we can. The first thing we need to do is turn all these into ones, right? So let me do some row operations on this. Let's see if we can turn this into row reduced echelon form. Okay, I'm gonna do kind of 3 steps at once here. What do I do to make this leading entry a 1? Yeah, multiply by 1/2. Do I agree with that? So I'm gonna multiply this by 1/2. This row by 1/3, right? And this row by -1. Do I agree with that? Let's see what shakes out. We now have this new matrix 1, 2, 3, 4, 5, 6, 7. The next matrix or the next row, it's not as nice. 1 minus 4/3, 0, 1/3, 4/3, and finally multiply by -1. I get 1 minus 4 minus 3 minus 2. And okay, so now all my leading entries are 1. And what else do I have to do? Well, I have to make sure that I've got to make sure that in every column we see a leading entry. This is the only non-zero entry. This column's good to go, right? This column not good to go because it's got zeros below it. It needed that for echelon form, but it's also got a 3 above. So how do we fix this? Just multiply this row by -3 and add it to this one, and that will kill that 3. Everybody agree with that? So multiply by multiply by 3 and -3 and add. So that's going to give me second row 0, 0, 1, minus 4/3, 0, 1/3, 4/3. And I'm not gonna be messing with this one either, so I'll just go ahead and write this down. Minus 4, minus 3, minus 2. Multiply this by -3 and add it up here. I get 1, 2, 0. Oh, let's see. Let's see, multiply by -3 and add, multiply by -3 and add, I get 8. Multiply by -3 and add, I get 5. Multiply by -3 and add, I get 5. Multiply by -3 and add, I get. Okay. And now, this column's taken care of, and this column's taken care of. What's left is this one. All right, this is the last one with the leading entry. So I follow the same procedure. I guess I got to multiply by 4/3 and add it here, multiply by -8 and add it. So. Yeah, I'm still going to have. Bottom rows, zeros. This is my operating row here, 0, 0, 0. 1 minus 4 minus 3 minus 2. First, I'm going to multiply this row by 4/3 and add to this row to kill this. So I'm going to have the row above 0, 0, 1, 0. Times minus 4/3 and add, so it's going to be minus 16/3. Times 4/3 and add, that's going to be, I guess that's going to be minus 4 1/3. So that's going to be minus 11/3. And times 4/3 and add, that's going to be minus 8/3, so minus 4/3 total. And I've also got to kill this 8. So I'm going to multiply by minus 8 and add. Minus 8 times this row and add. And so on the top row, I'm going to get 1, 2, 0, 0. Minus 8 and add. Let's see, minus 8 and add, that's going to be 32 and 5, it's 37. Minus 8 and add, that's going to be 24 and 5, it's 29. Minus 8 and add, 63. That is in row reduced echelon form. All my rows of zeros at the bottom. My leading entry of each row, they're all ones. They move down to the right, and the columns with the leading entry in them are barren except for the 1. Everybody okay with that? Now, here's a big theorem that I'm not going to prove this to you, but if you mess around with this, you will see that it's kind of true. It's basically just computational. There. Any matrix can be reduced via row operations to a unique matrix in row reduced echelon form. And we're going to do this, and we're going to do this in the context of solving linear equations here. Okay. By the way, let me, I'll do that definition. What does this mean? This means if I walk up to you on the street and hand you any matrix, then you can do your prestidigitations with it, mess around with it, doing row operations, and get something that looks like this. It's in row reduced echelon form. And what does the uniqueness mean? This is why this is useful. What that means is this. would everybody agree that when it start off with some matrix, you got a lot of different choices for the row operation, right? You might elect to swap these two rows. You might swap two different ones. You might take this one and add 3 times this to the 5th row. You might add -2 times the 6th row to the 2nd row. There's all kinds of different things you might do, right? No two people will probably do this the same way. But what it means is when you're done with your problem, you do row reduced echelon, you muck around with it till you get row reduced, and you do it as well, your answers better be the same. Because even though your processes are different, at the end of the road, if you start with the same matrix, you get to the same row reduced echelon form. Otherwise, you wouldn't be taking this class because it would be really useless. You always get down to the same form, row reduced echelon. If you go all the way to row reduced echelon form. Let me give you another definition, by the way. These are called pivot positions. They are the position in the original matrix or in the reduced matrix. They're the position where the pivots show up. And what is a pivot? A pivot is just leading non-zero entry. Right? In this case, I've got a I've got a 5-row by 7-column matrix. I've got 3 pivot positions because I have 3 non-zero rows. Everybody agree with that? And their columns are pivot columns. So the pivot columns here are columns 1, 3, and 4. Right? So pivot position is just a position in the matrix, either the reduced one or the original one, where those ones show up, the leading row entries, and the pivot columns are columns. Okay, any questions? Okay, so we're going to do this row reduced echelon form, but I want to do some more practice actually on systems of equations. So let me give you this equation here, or the system of equation here. Yeah. Suppose I have this. X1 plus 2x3 is equal to 2, and 3x1 plus 2x2 2x3 is equal to 5. And in this example, I want to put this in the augmented matrix and try to find a solution, if any. So, how do we tackle this thing? So I've got 3 variables. Everybody agree with that? So I need 3 columns for my variables and 1 for what's on the other side of the equal sign. 1, 1, 0, 1. Everybody see where that first row comes from? 1x1 plus 1x2 plus 0x3 is equal to 1. Right? 1, 0, 2, and 2. Right? And 3, 2, 2, 5. Now, let's commence to doing our thing. I'm digging on this one. I wanted to take out everything in sight. So I'm going to multiply this times -1 to take out this row, and then times -3, take out this row and add it. So let's see what we get. Same top. Times -1 and add, that's going to give me a 0. It's going to give me -1. It's going to give me 2. It's going to give me a 1. And times -3 and add, that's going to give me a 0. That's going to give me a -1. It's going to give me a 2. And that's going to give me a 2. might be a giveaway here, but how might I move on?
It's inconsistent.
Very good. How do you know that?
So the last two rows are essentially saying that minus x2 plus 2x3 equals 1. But in the second row, it's saying that the same equation equals 2.
That is correct. That is correct. He's saying this equation is, let me abbreviate further. Minus x plus 2y is Bill, minus x plus 2y is Fred, and Bill and Fred are different, right? This has to be inconsistent. But let's keep in mind that my parents were cousins, so when you humor me, I'll take another step here. 1, 1, 0, 1. So if I went further here, how could I reduce this further? I can multiply this by -1. That's a natural thing to do, isn't it? And this is going to actually reveal something for us that I think is very useful. So when I multiply by -1 and add, I'm going to get 0, 0, 0, right? 1. Everybody okay with that? When you have an inconsistent system like we had here, you can just go ahead like an automaton. This will always happen. Notice this equation is 0 equals 1, right? So whenever you have 0 equals some number that's not 0, that means it's not consistent. This is inconsistent. So let me give you a little figure. A system is inconsistent if and only if and induced a matrix with a row of form 0, 0, 0, 0, be not. So if you have an inconsistent system, you can reduce it. If you go through the motions of trying to get it into row reduced echelon form, you will eventually come up with all zeros equal a number. And you're like, hooray, it's inconsistent. You know that. And if and only if means it works both ways. If you ever get this, it's inconsistent. And if it's inconsistent, you have to get this, right? So that's kind of a nice thing to know, that you can just kind of go ahead on your bulldozer and just go through the motions, and you'll eventually come up with something like this if it doesn't work. Okay, any questions? Okay, let's do some more of this. Here. Yeah. So let's do another system here. Let's do this one here. X1 plus 2x2 minus x3 plus 2x4 equals 6. 7x3 plus 4x4 is equal to 1. 2x1 plus 4x2 plus x4 is equal to 4, and x1 plus 2x2 minus 5x3 minus 3x4 is equal to 0. Now this one is going to have sort of a few more solutions, and I kind of want to explain to you how to parameterize. By the way, before I do this, let me do something a little bit simpler before I dive into this complicated. Listen to this. How would you find solutions to this? How many solutions do you think? Actually, it does have into many, because this is a line, isn't it? So if I were to do, so here's a silly kind of thing. If I were to put this in matrix, it would be 1, -3, 5. And somebody tell me, what's this row reduced echelon form? It's already there, right? There's only one row, and my leading term is a 1, so lucky me, it's already there. How many pivots does it have? One. This is the pivot element, or this is the pivot position, and it's the pivot column, right? Silly columns, only got one thing. So how do you get this, right? Well, there's infinitely many solutions. Don't expect to just write down a handful of things, right? Here's the way I write a solution. X2 can be anything. This is called a free variable. Free variables are actually going to conform to the non-pivot columns. And X1 is 3x3, I'm sorry, 3x2 plus 5. This is the best way to describe our solution, because it's just like points on a line, right? X2 can be anything. And once you know X2, you know X1, because this is what makes it work. For example, if X2 is 0, the next one is 5. If X2 is 46, and I wish I had picked that, the next is 143, right? Like that. You just take whatever X2 is and you plug it in, that tells you what X1 is. This is called parameterizing the solutions, right? You just let X2 run willy-nilly all over the place, and given a plug-in value for X2, you get X1. Sometimes you have to plug in more values. Where do you suppose it would be if I had this? If I wrote this in a matrix, it would all similarly be kind of silly. Again, one pivot, and that corresponds to what we call a basic variable as opposed to a free variable. How many non-pivot columns do I have in not the augmented part, just the variables part? I've got 2 non-pivot columns, right? This is what we call 2 free variables. That means in this case, X2, X3 are free. So you've got 2 degrees of freedom, right? You can let X2 be whatever you pick, you can let X3 be whatever you pick, and this determines X1 because it is X2 plus 2x3 and then tack on 1. So for example, if you pick X2 to be 1 and X3 to be 2, then you get X1 is 6. Right, okay? Okay, so let's take this new bit of knowledge and let's throw it at the system here. Do a couple of things to this. Let's look at this one. Let's make our augmented matrix. 1, 2, minus 1, 2, 6, 0, 0, 7, 4, 1, 2, 4, 0, 1, 4, and 1, 2, minus 5, minus 3, 0. Now I'm going to use, I notice I see a 1 here, that's very convenient. So in my next step, I'm going to leave the top row alone. And I'm not going to mess with the bottom. I've already got 2 zeros right there. What do you suggest? Here. Yeah.
Multiply the first equation by -2 and add it to this.
Yeah. Let's do this first row by -2 and add it here. And so that's going to buy me 0, 0. times -2, right? So that's gonna be 2 and -3. And don't forget this, times -2 and add is going to be -8. And this one's a little bit more obvious, I think, maybe. Multiply it by -1 and add it to this, which is going to give you 0, 0 again, right? And -4, -5, right? And -6. Okay. Well, now I'm just following sweep this out here. You know what I'm gonna do? You don't have to do, so this is me pointing out that we many ways to do it. Of course, the easiest thing maybe is to multiply this by 1/2, which is kind of a pain, right? But here's what I'm actually gonna do. I'm going to, this shows you that there's more than one way to skin a cat. If you want to be sort of formalistic about it, you can probably just multiply this by 1/2 and you've got a 1 and you just have to take this out. I'm gonna do this. I'm gonna leave the third row alone. I'm gonna multiply this by 2 and add it here. And so bottom row is gonna be 0, 0. Let's see, times 2, that's going to be 0. Times 2, that's going to be -11. Times 2 is going to be -22. Right. And because I'm too lazy to deal with fractions, I'm going to multiply this by times -3 and add here. Anybody know why I did that? Why would I multiply this by -3 and add it up here?
I had 22.
Basically, if you've ever heard of it, I'm using the Euclidean algorithm, but it turns this into a 1. Right, so that's another way you can do it. Comes -3 and add it here, that's going to be 0, 0. 1 comes -3 and add it here, it's going to be 13. Comes -3 and add it here, it's going to be 25. Notice this one reduces nicely, right? I mean, for sure, what I need to do is divide that by like -11, right? And so let's do that. 1, 2, -1, 2, 6, 0, 0, 1, 13, 25, 0, 0, 2, -3, -8, 0, 0, 0, 1, 2. I'll leave my original equation here. So now I'm poised to strip everything down. And the easiest way for me to do it, I think I'm gonna start here. I'm gonna use this one because I'm going for row reduced echelon form, right? Notice that this isn't quite an echelon form, right? Because these two leading entries are in the same column. But I actually want to do row reduced echelon form. So I'm going to use this 1 to take everything in the column above it out, right? I'm going to multiply it by 3 to hit that out. I'm going to multiply it by -13 to take that out. And I'm going to multiply by -2 to take that out. And so what that's going to buy me is multiply by 3 and take this out. I'm with 0, 0. 2, 0, -2. Correct. And comes -13, and I get totally lucky on this one. 0, 0, 1, 0. That's -13 and add 0. That's going to be -26 and 25 is -1. And finally, comes minus 2.5. That's going to give me 1, 2 minus 1, 0, 2. Anybody see something I can do here? It's still not in row reduced echelon form. I'm actually gonna not write this whole matrix again. What can I do to this row to make it easier?
By the third row by 2.
Good, let's multiply this third row by half, right? Divided by 2, right? Okay with that? Now, what do you say? What can we do now?
Just kind of switch this.
You can squish these out, right? You multiply this by minus 1, that this is gone. So I'm actually going to get a row of zeros. So actually, to save you writing another matrix, everybody agree when I multiply this by -1 and add it to this, I get a row of zeros. Now, my row reduced echelon form says, hey, Jim, you got to move that row of zeros to the bottom. So in my next step, I will do this. There's my row of zeros. So I've got this one checked out, the form for the row. Then I want to have 0, 0, 0, 1, 2. I'm going to have 0, 0, 1, 0, minus 1, and 1, 2, minus 1, 0, 2. That's not one. Almost not quite. Is this row reduced echelon form? What's the missing piece of the puzzle here? Columns. Well, here are my pivots. And they're all ones. They move down to the right, so we're good to go there. But this column is all zeros. This column is all zeros except for the pivot. This one's the only defective one. So to finish this off, all I've got to do is just add this. That. And so in finished form, my row reduced echelon form for my matrix is this. Got a row of zeros. I've got 0, 0, 0, 1, 2, 0, 0, 1, 0, minus 1. But when I add it up here, I'm going to use 1, 2, 0, 0. Everybody okay? How many pivot columns do I have? The pivot columns, basic variables, they're the ones that can be written in terms of the other variables because in that they only appear in that equation. How many non-pivot columns do I have? And remember, I'm only talking about over here to the left of my dividing line. I've got one free variable. One non-pivot column. So let's write these equations down and we'll get the solution. So what are the solutions? Well, now that we've reduced this, let's write a much easier set of equations. This last equation is 0 equals 0. I don't think I'll like that, right? This equation is x4 equals 2. So in this system of equations, the x4 always got to be 2. This equation is x3 is equal to -1. These are my basic variables, right? I've determined them completely. And I've got one last equation, and that is x1 plus 2x2 is equal to 1. Now, x3 and x4, I totally nailed down. This last one has infinitely many solutions, right? So the whole system has infinitely many. And so the way I would write the solution down is x1, the last basic variable, is minus 2x2 plus 1. So I'll write the solution this way. X2 is free because it corresponds to the non-pivot column. X1 is minus 2x2 plus 1. X3 is negative 1. And X4 is 2. Everybody see that? So that is a complete description of all the infinitely many solutions to this system of equations. Okay. Any questions on that? Yes.
Yeah, so in terms of the vocabulary, I just want to make sure I got the stuff from last class correct. It would be consistent but not unique, right?
Yes. Consistent whenever you've got any solution whatsoever. This is a consistent system, and it's not unique because we actually have infinite solutions. Okay. Other questions? Okay. Any other questions? All right. Let me give you a quick example where I'm not going to go into the particular details of this one. I'm going to show you the start and end game. So if I give you this example here, x2 minus 3x3 minus x4 is 2x5 is equal to 1. Minus 2x1 minus 4x2 plus x3 plus 2x4 plus 3x5 equal to 5x1 plus 10x2 minus 7x3 minus 5x4 plus x5 is equal to 3 and 5x3 minus 4x5 is equal to 2. Now, here's what I'm going to do here. I'm not going to go through all the matrices. I think it's important you guys do this on your homework, by the way. I know that it probably seems silly and childish to work through this, but it's just like doing a sport. You know, if you want to be good at basketball, you got to hit the court, you got to do the, you can't just watch it on TV. So try to work through this example here.
I did have a question actually
Yes.
about like calculators. So on homework, some calculators can do this. What extent are calculators allowed on our exams?
On your exam, no calculator.
So calculators, well, okay,
Yeah.
and then on the homework, obviously.
On the
doing it-
homework, you can do whatever.
Right.
Sometimes it won't help you because a lot of times I do things in terms of parameters or whatever.
Okay.
But I mean, so the default is you can use what you want, and I'll let you know if there's any restrictions later.
But not on the exams. Okay.
Yeah, but yeah, I just won't use one test. Okay, so if I were to ask you to find the solutions to this, I'm going to give you the start, and I'm going to give you what I got at the end game, going through all the process. So I'll start with this matrix here: 1, 2, minus 3, minus 1, 2, 1, minus 2, minus 4, 1, 2, 3, 2, 5, 10, minus 7, minus 5, 1, 3, 0, 0, 5, 0, minus 4, 2. Everybody in agreement? Okay. So in the end game, this is what I got. I got that it was consistent because I never got one of those funky rows. Well, I played around with this and did the row operations. And even if you don't do the same ones I do, remember, we've got a theorem that says, if you work through this problem, if you get something different than what I got, one of us is wrong. Right? Because we have to get the same answer. I got this. 1, 2, 0, minus 1, 0, 3, 0, 0, 1, 0, 0, 2, 0, 0, 0, 0, 1, also 2, and I got a row of zeros. Okay. So what I want to do now is I want to kind of analyze and see, what we expect to get out of this. How many pivots do I have? Oh, would everybody agree I'm in row reduced echelon form? Right, I've got everything I need. My row zeros at the bottom. I've got ones, they're going down to the right, and the columns are all zeros except for ones. Right? How many pivots do I have? Okay, I've got 3 pivots. Basic variables. And so I've got however many's left over, I guess 2, corresponding to these 2, I have x2 and x4 are free variables. Everybody understand where I get that? Because this is a non-pivot column, this is a non-pivot column, and they correspond to variables x2 and x4. So this is one of the ones where we require more than one parameter. So my final equations, it looks like, are x1 plus 2x2 minus x4 is equal to 3. X3 is equal to 2, and x5 is equal to also 2. So this is my solution set. So here's what happens. The way I will write this is I would say x2 and x4 are 3. And what I mean by 3 is you can go through and plug in any 2 values that you want. Anything you want for x2, anything you want for x4. And x1 is determined by these. This is equal to minus 2x2 plus x4 plus 3. And then the other 2 variables, so I got 2 free, they're telling me what x1 is. And the other 2 have to both be 2. There's your solutions. Okay, any questions? Well, I'm going to delve more deeply into something that we call vectors next time, but let me ask you this. I'm curious as to what your all's experience is. How many of you have seen anybody ever played with vectors before? Maybe not even in math, but physics class, or you balancing forces or whatever. Like for example, in the plane R2, you draw these vectors. So tell me if this is familiar to you all. This is vector 3, 4, so I go over 3 and up 4. Like this. And this is vector -5, 2, so maybe it's right here. And you can add them up just by adding coordinates separately. Have y'all seen this before? Maybe just a little familiar. And with that vector there, how many of you ever done that head-to-tail vector addition or the parallelogram law? Okay. Good. We will delve into that next time. Any questions? I will be posting your first quiz. It will be due like by 5 o'clock on Tuesday. All right, so